Thank you for joining us today. My name is Kathy Sheffers, and I'm with Goodheart-Willcox Publisher. Goodheart-Willcox is really proud to support HVAC educators with quality instructional resources designed to help prepare your students for entry-level HVAC careers. Today, I am happy to introduce you to one of our outstanding authors. Xavier wrote Math for HVACR, which provides a review of basic math and advanced calculations within a framework of HVAC applications. In the book, Gary has done a wonderful job explaining why HVAC technicians need to know the material. Gary was also instrumental in the development of GW's new Follow the Heat animations, which are available with the 21st edition of Modern Refrigeration and Air Conditioning by Dan Braciano and the new 5th edition of Heating and Cooling Essentials by Don Crawshaw. These two textbooks also include online interactive troubleshooting activities for students. During his presentation today, Gary will share strategies and best practices for teaching those important troubleshooting skills to aspiring HVAC technicians. So now I'm happy to turn it over to Xavier.
Thanks, Kathy, and I'm happy to be here as well. I want to talk a little bit before we start this program about how teaching troubleshooting tactics came about. About 20 years ago, I was just starting out as a teacher, as an instructor after 20 some odd years in the service field, servicing chillers and boilers. And I got a call from a potential customer. And the call was a little confusing because he said, could you do a class and teach my mechanics how to troubleshoot? And I said, sure. Troubleshoot what? And he said, everything. The gentleman I was talking to was a maintenance director at a major pharmaceutical company. And I stopped for a moment and thought about what he said. And I said, wait a minute, are you talking electrical things? Are you talking mechanical things? Heating, cooling? What are you talking about? He said, I'm talking about everything. We seem to be buying a lot of spare parts over and over again. And I think that my mechanics are doing more parts changing than they are troubleshooting. Can you help me with that? So I told him I would give it some thought. And I did. I thought about it for a day or so. And I called him back and I said, I have a program in mind for your mechanics. And he said, what's it about? And I said, logic. And it was a big pause. And then he said, logic. And I said, yes, troubleshooting is based on logical thinking. So we need to teach them some logic. And he said, if I tell my mechanics they're going to come to a class about logic, no one will come. And I said, well, we're not going to tell them that. We're going to tell them it's about troubleshooting. And that's what troubleshooting is. It's based on logical thinking, thinking through a problem. That was over 20 years ago. And I've used that program and revised it several times since. And that's what we're going to talk about today is how do we teach it, but more so, how do they learn it? There's a big difference there. I often say that we can't teach someone how to be a troubleshooter, but they can learn how to be a troubleshooter. The reason I say that is because we all learn differently. We all process information differently. So we know how to troubleshoot perhaps from our own way of learning it. We can teach the students or ourselves how to troubleshoot, but everyone has to learn it on their own. So that's what we'll talk about. I call it teaching troubleshooting tactics. Welcome to that, and welcome to the heat transfer business, because that's what we do. We are in the heat transfer business. Those of you that have been with me before for other presentations realize that I say that a lot. We are in the heat transfer business. It's what we do. We move heat around. We move heat around for heating, we move heat around for cooling, but it's what we do. So let's talk about how we troubleshoot those systematic problems. Troubleshooting, if we look it up in the dictionary, is a verb that says this: to act or be employed as a troubleshooter, to deal with in the capacity as a troubleshooter. Troubleshooting is a form of problem solving often applied to repairing failed products or processes on a machine or a system. It's a logical, systematic search for the source of a problem. A logical, systematic search for the source of a problem in order to solve it and make that product or process operational again. Isn't that what we do? Isn't that what we do all the time? We have to think logically through the process to figure out what caused this. Don't just fix the problem, fix the root of the problem. That's what troubleshooting is all about. Troubleshooting is needed to identify the symptoms of that problem. We all know the difference between a parts changer and a troubleshooter. A parts changer changes parts in the hopes that they will fix the problem. A troubleshooter determines the cause of the problem, and then if they need to replace a part, they do so. That's the difference. Troubleshooting is determining the most likely cause of a process. It's a process of elimination, eliminating potential causes of a problem. Again, these dictionary definitions go right to the heart of what we do as a trade when we try to repair a problem with a system. Troubleshooting requires confirmation that the solution restores the product or the process to its working state. How many times have we heard avoid callbacks? We want to make sure we fix this problem the first time. Confirmation that we've restored the product or the process to its working state. That's what we want. That's what we want in troubleshooting. A troubleshooter, according to Mr. Webster, the dictionary guy, says it's a person with a special skill in resolving disputes, impasses, etc., as in business, national, or international affairs. For example, a diplomatic troubleshooter in the Middle East. I certainly wouldn't want that job. But an expert in discovering and eliminating the cause of trouble in mechanical equipment, I'll take that job willingly. That's what we do. Yes, we're in the heat transfer business, but to keep that heat transferring, we have to make sure we can find the problems, solve the problems, fix the problems, and hopefully keep them from reoccurring. That's what a troubleshooter does. So when I started out, almost 55 years ago now, it's been a long time, but when I started out looking at this equipment back in the 1960s, not the 1860s, but the 1960s, but when I looked at this first equipment, I was a parts changer. I didn't know it. I really didn't know that's what I was until somebody said that to me one time when I was a younger man and said, you know, you change a lot of parts. Do you know what you're doing? Very honestly, I wasn't sure I did. But what makes a parts changer into a troubleshooter is something that took me a while to figure out. And what it came down to in my way of learning it was what I call the 5 steps.
Troubleshooting. Troubleshooting, as I often tell my students, can't be taught. It can only be learned. While that may sound contradictory, I simply mean this. Everyone processes information differently, and a procedure that may work for one technician may not work the same way for another. So, while I can't teach them to be a troubleshooter, they can learn to be one. What I found as I learned to be a troubleshooter was I used 5 steps to hone my troubleshooting skills. Step 1. Observation. Observe. In other words, look before you touch. Before changing anything, observe the system's operation and compare it in your mind to your knowledge of how the system is supposed to operate. Is everything moving, turning, running the way it is supposed to? Look for any obvious signs of trouble. Noise, odor, smoke. Observe. Step 2. Think logically. Logical thinking is what separates humans from machines. We have the ability to logically think through a problem or a system. Think about the refrigeration cycle. Follow the heat through the system. Think about the pressure-temperature relationship. Think about the flow of electricity. Think logically through the process of heat transfer. Step 3. Establish a pattern. Always troubleshoot a system in the same order. Use the same pattern so you won't forget anything. If you always start by looking at the evaporator, then always do it the same way. Whatever pattern of steps seems to suit you best, do it, but always do it in the same order. Step 4. Accept help. Never be too proud or too sure of yourself to be afraid to ask for help. Ask other technicians, ask distributors, ask manufacturers. Every piece of equipment sold has a manual, and that manual nearly always has troubleshooting information in the back of the book. Use it. Step 5. Practice, practice, practice. It takes years to see all the HVACR system types there are, and new variations appear almost daily. So practice is the key to becoming a reliable troubleshooter. Troubleshooting is not something that can be mastered in a day, or perhaps even a year. But over time, with enough practice, skills can be acquired to make nearly anyone a troubleshooter, rather than a parts changer. Troubleshooting, a skill that can be learned but not taught. Don't be discouraged. It takes time, practice, and experience. Just remember to follow the heat. Troubleshooting.
5 steps of troubleshooting. Now, not everybody learns it the same, as I've said before, but the way I learned it was like this. I learned it to be 5 steps. Step 1 is observation. Observation. Pay attention to that piece of equipment. Observation. Observe. Before you start to tear something apart, look at its operation or inoperation. Is it running at all? Is everything doing what it's supposed to do? Look at everything. So observation, number 1. Number 2, think logically through the problem. Think about follow the heat through the refrigeration cycle. Think about the sequence of operation for a boiler burner. Think about the electrical circuitry. They're all logical. So think logically through the problem. That's number 2 in my 5 steps. Number 3, establish a pattern. Establish a pattern of how you troubleshoot and always do it the same way so that you don't miss a step. If you always start with the main power, then always start with the main power, which is a great place to start. But if you always start with the evaporator, then always start with the evaporator. Always start in the same place and work through that pattern so that you don't miss anything. Number 4, don't be afraid to ask for help. Don't be afraid to accept help. Ask for help. No one knows everything about every piece of equipment we work on. I've looked at thousands of pieces of equipment in my 50 some odd years, but I haven't seen them all, and I never will. I still get help with troubleshooting, help from the manufacturers, help from other technicians, help from my students. So I get help. We all can accept that help. And then number 5, practice, practice, practice. We say we practice troubleshooting. It's like practicing a profession. We always say a doctor is practicing medicine or an attorney is practicing legal work. Why do we say that? Because they're constantly learning, just as we are constantly learning. We're as professional as anyone about this. And we practice, 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 practice. So those are my 5 steps. And we're going to go into detail on each one of those as we go along here. But as I've said before, we can learn how to troubleshoot, but it's hard to teach it simply because everyone gathers information and processes that information in their own manner. Everybody's mind works a little differently. So we can show people how to do it. My 5 steps might not work for everyone. Other people might have a different procedure, a different process, a different way of thinking about it. But if we can show our students and show ourselves, number one, how to observe. Number two, how to think logically through the problem. Number three, how to establish a pattern. Number four, don't be afraid to accept help. And number five, just keep practicing. That's how we learn to troubleshoot. We teach it that way. So let's take a closer look at my 5 steps. Number one, we have to teach our students to be observant. We have to teach them to think about the operation of that equipment before they touch it. Sometimes it's pretty easy. Sometimes we walk up to a piece of equipment, it's not running at all. So we check our power. That's observation. Is there power to the unit? But observation is number one. So we have to teach them to back off just a little bit, wait for just a moment, don't rush into it, start tearing things apart. Observe, pay attention to the system. Observation. Observation sets the tone for how we address the problem, how we look at it. It forces our technicians to take a look at the big picture. We're trying to keep them from being a parts changer. I'll tell you a little story. Many years ago, I walked into a facility, an existing customer of mine. I was a contractor. I had, well, when I got rid of my business 20 years ago, I had over 350 buildings under contract to me, where we did the service work on their boilers, chillers, etc. And I went into one of the buildings one afternoon, and one of the chilled water pumps was not running. And as I walked in, chilled water pump was not on. One was, I had 2 in parallel, one was running, one was not. And so I immediately started to take the housing off the pump. And then I realized, well, before I do that, I should probably shut off the power. So I walked over to the panel and the breaker was thrown. That was not observation. I was trying to be a parts changer. I was going to dive right into that pump because it wasn't running. Had I stood back and observed for a moment, thought logically through the problem, logic would have told me, check the power source before you start to take the housing off the pump. And I didn't do that. So we can all learn, but we have to observe. We don't want to be a parts changer. We want to look for the obvious things. Look for the obvious. That's our first step, is observation. If the unit's not operating at all, start with the electrical supply, like I should have done with that pump. Start the electrical supply. But if the unit's operating and not performing properly, then start by determining what it's doing incorrectly. Is it not cooling? Is it not heating? What is it not doing? Is a fan not running? So pay attention to all of those things. And remember, look before we touch. Look before we touch. That's all part of observation. Number 2, logical thinking. We've got to teach our students and ourselves to think logically through the problem. Logical thinking is something we can learn. It is something we can learn to do. Again, we all do it a little differently, but we can learn it. If it's an air conditioning system that we're dealing with, review the refrigeration cycle in your head. Evaporator, compressor, condenser, metering device, follow the heat through the system, the change of state of the refrigerants. So think logically about how that system is supposed to transfer heat. And that may lead you to where it's not transferring heat. And that points you in the direction of what's wrong. On a heating system, think about the process of changing energy from a fuel to a heat, from chemical energy to thermal energy. Think about the sequence of ignition for the burner. As I said a few minutes ago, not everybody thinks about this the same way. Jason Orbit, that I know quite well, another instructor, in his 5 steps, said number one is check the thermostat. What a great idea. Jason learned it and teaches it a little differently than I do. But what a great idea. Check the thermostat. How many times have we found a situation, especially in residential and light commercial work, which I very seldom did, but where people mess with the thermostat? And we find that the only problem is the thermostat. So think logically through the system. Start at the beginning and think logically through that. Logical reasoning is a process. We need to use rational systematic steps to arrive at a conclusion about the problem. And the conclusions are based on what we see, based on given facts. There are a couple of types of reasoning that we study. And with your students, if you are an instructor following this program and want to use this in class, with your students, I would suggest this, that you don't want to spend a lot of time trying to explain the difference between deductive reasoning and inductive reasoning. You're liable to lose them, only because it tends to get boring. I know that myself. But we need to know about it because it's a difference in the way we think and process information. Deductive reasoning versus inductive reasoning, big difference here. Deductive reasoning, also called deductive logic, is the process of reasoning from one or more statements to reach your conclusion. Inductive reasoning is reaching a conclusion based on observation. So, from what I've already said this morning, you can probably tell which one of these is more beneficial to us as troubleshooters. Inductive reasoning, reaching a conclusion based on observation. Deductive reasoning, not as good for us, but let me show you the difference. Deductive reasoning links premises with conclusions. It goes like this. If all premises are true, the terms are clear, and the rules of deductive logic are followed, then the conclusion is true. That doesn't always work for us. It doesn't always work for us. Look at it like this. Deductive reasoning starts with theory. And we know we have to understand the theory of our operation. Don't get misled by that. But deductive reasoning starts with a theory and works its way down to the conclusion. We state a hypothesis based on our theory. A hypothesis is, well, we think this might be wrong. That's a hypothesis. We then do our observation and see if our observation leads us in the direction of our hypothesis. We want to confirm our hypothesis. That's deductive reasoning. Can you say parts changer? Because that's what a parts changer uses. A parts changer says, okay, my theory tells me it's doing this. Yeah, I think that's what it's doing. Let's change that part. That's a parts changer. That's deductive reasoning. That's how I started out 50 years ago. It doesn't work well for us. Believe me, it doesn't work well for us. I changed a lot of parts that I probably didn't need to change because I didn't know what I was doing. Inductive reasoning is logical thinking using observation and experience to reach a conclusion. Think about it. Observation and experience. What better way is there to be a troubleshooter than based on your observation and your experience? That's why I said before, practice is so important because our experience is going to count here. Inductive reasoning takes specific information from observation and past experience and makes a broader generalization that's considered probable, while still remaining open to the fact that the conclusion may not be 100% guaranteed. How many times have you heard yourself say, I think it might be this, but I'm not sure? Of course, because it's never 100% guaranteed that we've found the problem until we then make that repair and by observation see that, yes, that was the problem. So I'm going to repeat that underlined part. while still remaining open to the fact that the conclusion may not be 100% guaranteed. That's inductive reasoning. Inductive reasoning is making an educated or informed guess based on the information or data that's available. Observation and experience. Inductive reasoning. So inductive reasoning starts with observation, which is where I started my 5 steps. Observation. So we start with observation and work our way to a conclusion. We establish a pattern. We talked about that. Step number 3 in my 5 steps. From that observation and our pattern of looking at things, we then form our hypothesis. Our theory then is built upon that. And from that way, we become troubleshooters instead of parts changers. That's the difference between deductive and inductive reasoning. So, as I've said a number of times, everyone learns how to troubleshoot differently. But if you can show your students or yourself how to use inductive reasoning versus deductive reasoning, the result will be much better. Here's an example. We've all seen this. We've all seen something like this in our careers, if we've spent any time in the field at all. And though I did not work on small equipment, I didn't see too many A coils like this in my service work, I still saw frozen evaporators. So what caused the ice to form on this evaporator? I've often asked that question in classes where I was doing in-person classes rather than virtual classes. I would show a picture of a frozen evaporator and ask my students what caused the ice to form on this evaporator. And then I would just listen for the answers. And very often, the number one answer was low on freon, it's low on charge. That's a parts changer answer. That's a parts changer answer. I'll show you why in a moment. If we use inductive reasoning to think about this problem of ice on the evaporator, deductive reasoning will show us we just got to start adding freon. But if we use inductive reasoning, then we start with observation. Observation. What did I observe? I observed ice on the evaporator. That's my observation. So I look at my ice on the evaporator. And I look for a pattern. Where did the ice start? Is the entire evaporator covered with ice? And what causes ice to form? We know as HVACR people that ice forms from moisture that's below 32 degrees Fahrenheit. Water is above 32 degrees Fahrenheit. Ice is 32 degrees Fahrenheit or below. So, as you know, at 32 degrees Fahrenheit, we can have either. But when ice forms, it's because the refrigerant in that evaporator has a saturation temperature of below 32 degrees Fahrenheit. So to get the saturation temperature below 32 degrees Fahrenheit, the pressure has to be lower than it should be. On an air conditioning evaporator, we never want an evaporator lower than usually 38 to 40 degrees Fahrenheit. On a refrigeration evaporator, sure, they run below freezing all the time. But on an air conditioning evaporator, we never should see that refrigerant saturation temperature below 38 degrees Fahrenheit. It's too close to the freezing point of 32. So ice forming on the evaporator can be logically thought through as to why it was there. So it starts with observation. We look at that pattern. We form our hypothesis, which says low pressure in the evaporator. If that ice formed on that air conditioning evaporator, on that A coil, then the pressure in that evaporator had to be too low. That's what I call the root cause of the problem. And when I was teaching in front of a class, I always said that. I said, okay, look, think about the root cause. What is the root? How can you get ice on that evaporator? The only way you can get ice on that evaporator is if the saturation temperature of the refrigerant in the evaporator goes below 32 degrees Fahrenheit. And that's because of the pressure in the evaporator. It's because of the pressure and saturation temperature. That's inductive reasoning. So, once again, observation. Look for the pattern. Establish your hypothesis. And then look at the theory of it. So, low pressure in the evaporator. What might cause that? What might cause low pressure in the evaporator? Think logically. Don't be a parts changer. Parts changers start with the details. Troubleshooters start with the big picture and work their way down to the details. That's the way it works. So a parts changer might say, oh, low on freon, low on charge. But a troubleshooter says, low pressure in the evaporator. What could cause that? Well, when I would see ice on an evaporator that didn't belong on an evaporator, I always thought of it as low pressure. And what could cause that low pressure? There are three categories that I came up with that could cause low pressure in an evaporator: load, airflow, and refrigerant. Now, if we want to think of it logically, then isn't it logical to do the easiest ones first? To look at the easiest ones first? Why would I want to get out my refrigerant, get out my gauges, and start adding refrigerant to the system if I don't know for certain that that's my problem? That's not logical. So start with the easiest ones first. Look at the thermostat. Look at the thermostat. So, have you ever noticed that people mess with thermostats? Have you ever seen a situation where somebody says, well, I turned it all the way down because that way it'll get colder in here faster? They think it's a gas pedal, an accelerator. It's just a switch. It turns the system on and off. It's just a switch. But if they turn it all the way down and leave it turned down, and there's not enough load on that system probably wasn't designed to cool the room to 55, and the thermostat might go down to 55. So the unit dies trying. It just keeps trying to cool that space, and there's not enough load. And because there's not enough load, the pressure drops in the evaporator because the refrigerant's not changing state from a liquid to a vapor, and the pressure drops and it hits a lower saturation temperature, below 32 degrees Fahrenheit, and we ice that evaporator. Have you ever noticed by looking at the pressure temperature chart that, for example, on R22, between a typically charged air conditioner and a frozen coil, there's only a 10 psi difference. And on R134A, there's only a 7-pound difference. It doesn't take much of a drop in pressure to ice that coil. So check the thermostat. That's number one. What about the ambient temperature? If that unit ran all night and it was colder than normal outside, and it didn't have low ambient control on it or head pressure control, as your outside temperature drops, your condenser pressure drops, your head pressure drops, it can lower your inside pressure, your evaporator pressure enough to ice that coil. So I haven't had to use any tools yet. I haven't had to get my tools out of my toolbox. I haven't had to open the back door of my truck. I just am observing things. This is one that actually one of my students came up with years ago. I was writing this on the board, as I've done for years and years, and I was writing things down, and he said, What about a stuck contactor? I had that happen last week. And I said, wow, there's one I hadn't thought about. So I didn't know where else to put it. So I put it in the load section because it's kind of like a false load. But the contactor in his situation, the contactor is stuck closed. So the compressor continued to run even though the thermostat wasn't calling for cooling. Wow, what a find. So simple problem, but it pulled the pressure down nice the coil. So do the easiest ones first. Do the easiest ones first. That's thinking logically. If it's not load, then we go to the next easiest group, and that's airflow. Airflow. So a dirty filter, the #1 cause of ice on an air conditioning coil is a dirty filter. Lack of proper airflow, #1 cause, a dirty filter. I had a gentleman in class answer this question for me one day. I said, how do you know when it's time to change the filter on an air conditioner? And that gentleman said, well, when it gets sucked into the evaporator and covered with ice, it's probably time to change the filter. And he was making a joke, of course. He knew better. But I thought, wow, how many times have we seen that the filter is so dirty that it gets pulled into the coil and the whole thing ices up. Lack of airflow, dirty filter, #1 cause of problems on our air conditioning system. #1 cause. Logical thinking. A dirty evaporator coil. Anything that affects the airflow. The fan motor, the fan belt, the fan blades, anything that affects airflow. So look at all of the air side. Anything that affects the airflow. It could be a damper out of position in an air handler, a stuck damper. It could be an obstruction. I've seen insulation drop down where we insulate the inside of the ductwork and it comes unglued and it drops down, turning vanes out of position. So anything that affects the airflow. So logical thinking, load, airflow. Now, if it's not one of those, then and only then would I put my gauges on. I haven't even talked about those yet. I haven't talked about a set of gauges because so far I didn't need them. I know I've got low pressure in the evaporator. I don't need a gauge to tell me that because if I've got ice on that evaporator, I've got low pressure in that evaporator because it went lower than my saturation temperature of 32 degrees Fahrenheit. On an AC system, that's too low. But how do I know what my high side pressure is? So I've got to put my gauges on now. That's why I said before, if someone sees that ice and jumps to the conclusion of low refrigerant charge, that's a parts changer because they don't know their high side pressure yet. If they look with their gauges on, they know their low side pressure is going to be low because they've got ice. But if they look at their high side pressure and that's low as well, okay, then get out your leak detector because you've apparently had a leak or you've lost charge somehow. So then and only then do you think about adding refrigerant to the system. But you've already eliminated all the other causes that might have been easier to repair, such as a dirty filter. So what else could affect the low side pressure, but not make the high side pressure low? What about an obstruction? What about something between the high side and the low side? What's in the liquid line between the high side and the low side? The filter dryer. Maybe the filter dryer's plugged. Maybe the receiver has got a problem. If it has a receiver on it, maybe the king valve is closed. Who knows? But we check these things. Maybe it's the expansion valve. Maybe there's a problem there. So anything that's between the high side and the low side now, between the condenser and the metering device, is going to show us perhaps where the problem is. Maybe there's a solenoid valve in the liquid line. Some of our refrigeration systems have those, where we use hot gas bypass, for example, but maybe it's a solenoid valve that's closed. Maybe it's damage to the liquid line itself. I've seen liquid lines that somebody somehow managed to put a foot on them or something, and they squashed the line down a little bit, and it made a restriction in flow. So logically think through that problem. And if we use inductive reasoning, it brings us to that conclusion based on observation and our experience. That's the difference between being a troubleshooter and a parts changer. It's all about thinking logically. Always start with an HVACR system with the refrigeration cycle as you want to think logically through the system. Think about the refrigeration cycle. Evaporator, compressor, condenser, metering device. That's our cycle. That's how we live in the heat transfer business. Evaporator, compressor, condenser, metering device. And if your students or yourselves are not familiar with the cycle, memorize it. Commit it to memory. I often tell my students, there's only one thing you need to memorize in this business, and that's this right here. Once it's complete, then we memorize it. Evaporator, compressor, condenser, metering device. And to help us understand it, I always describe it like this. Put a dotted line through the center horizontally, through the center of the compressor and the center of the metering device. And everything below that dotted line is what we call the low side. We call it the low side, but it's low pressure and low temperature. Low pressure, low temperature. We call it the low side. And then everything above the dotted line is pretty obvious. It's the high side, high pressure, high temperature above the dotted line. Also, everything below the dotted line is considered to be inside the conditioned space. The evaporator is inside the conditioned space, and the condenser, of course, is outside the conditioned space. We know in real life, it's not always that exact. This is a theoretical line. In real life, the condenser and the compressor are outside the conditioned space, and the evaporator and the metering device are inside the conditioned space. But theoretically, that line has to go right through the middle. And then we give it a left side and a right side. And everything to the left of the vertical line is the vapor side. And everything to the right is the liquid side. So we end up with 4 sides to our system. 4 quadrants or 4 corners, you might want to think of it. We've got the low side, the high side, the vapor side, and the liquid side. In the bottom right corner, low pressure, low temperature, saturated liquid. In the bottom left corner, low pressure, low temperature, superheated vapor. In the top left corner, high pressure, high temperature, superheated vapor. And in the top right corner, high pressure, high temperature, subcooled liquid. So 4 corners, 4 quadrants to our cycle here. As the refrigerant moves through the system, in this case, it's going clockwise. As it moves through the system, every time it crosses a dotted line, something changes. When we cross the horizontal line, the pressure changes. When we cross the vertical line, the state changes. So every time we cross a dotted line, something changes. I also always teach my students to memorize, of course, the tubing, the piping that holds this together. Memorize the names to that because we talk about them all the time in the field. So coming out of the evaporator, going into the compressor, the refrigerant gets sucked into the compressor through what we call the suction line. The suction line. And then the compressor squeezes the refrigerant and we discharge it out to the condenser through what should be called the discharge line, but we commonly call it the hot gas line because we call it what's in it. High temperature vapor, hot gas. The designers call it the discharge line, but the mechanics call it the hot gas line. And then coming out of the condenser and going all the way back to the metering device. We call that line by what's in it as well. We call it the liquid line. The liquid line. So there is our cycle. And I've said for many, many years, if you can remember the cycle and learn how to follow the heat through that cycle, you can diagnose any problem with any HVACR system simply by looking for where the heat stops. The heat starts at the conditioned space, gets absorbed into the refrigerant in the evaporator. The refrigerant in the evaporator carries the heat to the compressor. We squeeze it, send it out to the condenser, and the condenser gives up the heat to outside the conditioned space. The refrigerant, having given up that heat, goes through the metering device or expansion valve, drops in pressure, hits its saturation, drops in temperature, and heads back to the evaporator to do it all over again. So we pick up heat at the evaporator, we pump it around, we give up heat at the condenser. Pick up heat by changing the refrigerant from liquid to vapor. Give up heat by changing the refrigerant from vapor to liquid. Liquid to vapor, vapor to liquid, liquid to vapor, vapor to liquid, over and over and over again, 1,000,000 times a day. That's how these systems transfer heat. So knowing that, we can use that with our logical thinking through our problems. So it starts with knowing the refrigeration cycle on the AC side, on the refrigeration side. There is one more line I just put up on this slide. It is the actual inside-outside line. It's the green line. I'll take it off and put it back on so you see it. It's right there. It's the actual line for inside-outside the conditioned space. The red line is theoretical. The green line is actual for, say, a split system, etc. When I talk about the refrigeration cycle and following the heat through the system, think of it as a process of steps in the heat transfer. If it's a system like a window air conditioner or a rooftop unit or an air-cooled air cooling system, it's only 2 steps. The heat goes from the conditioned space to the refrigerant in the evaporator, and then from the refrigerant in the condenser to the outside air. So it's just 2 steps. If we use a water-cooled condenser with a DX evaporator, it becomes 3 steps. The heat goes from the conditioned space to the refrigerant at the evaporator, from the refrigerant to the condenser water at the condenser, and from the condenser water to the outside air at the cooling tower or down the drain or to a pond or a lake. So it is 3 steps now. If it's a chiller system with chilled water, it becomes either 3 or 4 steps. With a chiller, the conditioned space air gives up its heat to the chilled water. That's the first step. Then the chilled water brings the heat to the refrigerant in the evaporator of the chiller. And then from the evaporator, we take the refrigerant to the condenser. If it's an air-cooled condenser, then we give up the heat to the outside air. But if it's a water-cooled condenser, it becomes 4 steps. The heat goes from the conditioned space to the chilled water, from the chilled water to the refrigerant, from the refrigerant to the condenser water, and from the condenser water to the outside air. So it can be 2 steps or 3 steps or 4 steps or more. I've seen systems with 5 or 6 or 7 steps because they added extra heat exchangers in there. But it's just logical thinking to follow the heat through the system. Follow the heat through the system. It makes good sense. So we want to know that for air conditioning and refrigeration systems. On heating systems, we're still in the heat transfer business, but it's actually a little simpler. On heating systems, think about the process of changing that fuel, chemical energy, into a fire, thermal energy. And then think about the process of making that happen. And that leads us to our sequence of operation of a burner. It's logical to think through this step by step. This is our sequence of operation. Now, for small burners, it's still going to be the same sequence, still going to be the same number of steps, but not as many items in each step because it's a smaller burner. For larger burners, maybe even more of each item in the step, but the sequence is the same. It always starts with a call for heat. We then have to prove our permissives. Our permissive is anything that has to give permission for that burner to light. We purge, we send air through the furnace and up the stack to make sure there's no unburned fuel. We then try to light, what we call the ignition trial or the flame trials. Once we've lit and can prove it, we're in the run period. The burner runs until something tells it to shut down. And then we go into our post-purge. So the sequence is always the same. The timing might be a little different, but the sequence of operation never changes. It's the only safe way to start, run, and stop a burner. So if it's a heating system problem, think about the sequence of operation. It starts with a call for heat. The operating limit closes. Closes to an electrician means conducts electricity. Open means breaks a circuit. Close means makes the circuit. The operating limit closes. Once that happens, it initiates our proving of our permissives. You might have 1 or 2 permissives on a small burner. You might have a dozen on a big boiler burner. But the permissives are anything that have to give permission for that burner to run. They all have to prove. The fuel valve interlock has to prove closed. The blower motor has to, and we need fuel, we need air. We have to prove both of those things. If it's a modulating burner, we want it to make sure it can ramp up to high fire, but we're going to light it in low, but we'll drive it up to high, bring it back down to light, but we want to make sure it can move. The running interlock circuit has to prove closed. On a boiler, the running interlock circuit would include things like low water level, maybe high water level, low gas pressure, high gas pressure, oil temperature, boiler pressure itself, air coming into the boiler room. So a lot of running interlocks there. They all have to prove closed. Closed means conducts electricity, completes the circuit. The high fire purge interlock has to prove closed. There might be only 1 or 2 permissives on a small burner. There might be a dozen on a larger burner, but they all have to prove that it's safe to try to light that burner. And then we send air through the furnace and up the stack. It might last 30 seconds, might last 3 minutes, but it's called the pre-purge. We send air through the furnace and up the stack to make sure there's no unburned fuel. Once we've done that, then we can try our ignition. On a small burner, there will be no pilot. You'll light direct to the main flame. But on a larger burner, you're going to have a pilot that lights first, and then we light the main. We don't use standing pilots on the big things anymore. There are still some used on our smaller equipment, but a standing pilot is one that we light manually and it stays on. We generally use intermittent pilots on the large equipment now, or we light direct to the main on smaller equipment. But regardless of how it's done on that particular burner, the sequence will be the same. We will have a call for heat, prove our permissives, do our pre-purge, and then try to light the burner. In this example, this is for a larger boiler burner, such as I worked on most of my career. Pilot valve opens, the ignition's on, we light the flame. Once we've lit the pilot and can prove it, then the main valve opens, we light the main off the pilot, and we have to prove it. And once we've proven pilot and proven main, then we go into our run period. The burner's on, the running interlock circuit is monitoring the operation of the entire system. If anything goes wrong, and one of our running interlocks opens, not enough water in the boiler, not enough air, too much pressure, too high of a temperature, if any of those things happen, that's a running interlock. If one of those opens, it shuts us down. If none of those happen, if everything is okay, it runs until the operating limit says, okay, shut us down. Then we go into our post-purge. The fuel valve's closed, the burner's off, the blower stays on. We send air through the furnace and up the stack to make sure there's no unburned fuel. So this is your sequence. So once again, for air conditioning and refrigeration systems, as we think logically through the problems, think about the refrigeration cycle, think about following the heat. For a burner, for a heating system, think about the sequence of operation, think about changing the fuel to a fire, and the sequence of operation that makes that happen. That's logical thinking all the way through. There's 2 things we have to deal with as HVACR technicians, and they're both logical. There's 2 things we have to deal with. Number 1 is electricity, and electricity is logical. It's logical. Right? I've always said it would be easier to teach an electrician the HVAC business than it would be would be to teach an HVACR person the electrical business, because electricians are taught to think logically. Circuits are logical. So we have to think about that. We have to think about that. So a study of electricity is critical. Circuitry, series circuits, parallel circuits, combination circuits, contactors and relays and thermostats and motor starters, all these different things, capacitors and transformers. We have to think about all these things. It's all part of troubleshooting, but electricity is logical. That's number one. And number two, the other thing we have to deal with all the time that's also logical is math. Math is logical as well. All of these things go into that logical thinking. So when we teach how to troubleshoot, one of the things we've got to teach is math, because math is logical. How many times do we use it? We use it here, the psychrometric chart. We use it right here all the time. If we're doing anything on the air side, we use it for the pressure temperature relationships, coefficients of performance, SEER numbers. Anything we do, we're using math all the time. And math is logical. Math is logical.
Ohm's law math. In the early 1800s, German scientist George Ohm discovered that 1 volt of electromotive force can push 1 amp of current through 1 ohm of resistance. This relationship is called Ohm's law. Ohm's law states E, electromotive force, or EMF, equals I, current, times R, resistance, or voltage equals amperage times ohms. A simple pie chart, often called the Ohm's law wheel, helps explain the algebraic formula of Mr. Ohm. If 2 of the 3 values are known, the unknown value can be easily determined by a little bit of algebra. Using the Ohm's law wheel, envision the horizontal dividing line as an equals sign and the vertical dividing line as a times sign. Thus, we can read it as 1 volt equals 1 amp times 1 ohm. Algebra allows formulas to be realigned depending on which value needs to be determined. So E equals I times R can also be written as R equals E divided by I. If 2 values are known, such as voltage and amperage, the third value, in this case resistance, can be calculated. For example, in a circuit with an EMF of 120 volts and a current of 2 amps, the resistance would be E, 120 volts, divided by I, 2 amps, thus 60 ohms. Ohm's law makes it possible to calculate unknown electrical values, which can be a great help in troubleshooting electrical circuits and components. Ohm's law math.
I like math. Probably pretty obvious, seeing how, as Kathy said before, I wrote the Math for HVACR book. I did that for a reason. When I first started teaching 20 some odd years ago, in my first semester of a brand new job of being an instructor instead of being a mechanic, my first semester, I found that my students couldn't do basic math. They were having a hard time with things like proportions and cubic feet and all these different things that we do. So I started teaching them math, and I didn't have a good book to work from. I couldn't find one. Grade school math book was too elementary, and a college math book was too advanced, and there was really nothing in between that I could find that worked. And years later, Goodheart-Willcox came along and said, "Could you write a math book for HVACR people?" And I said, "Well, where have you been all my life?" But that's what we did. So it's logical. It's logical. Number 3, teach your students to establish a pattern of how they troubleshoot. If you jump around, you're going to miss something. So we always try to do it in the same order. I remember the refrigeration cycle from the way I taught it. and still do. Evaporator, compressor, condenser, metering device. But yet when I was doing my service work, I didn't start at the evaporator. That might sound strange. But keep in mind, I was a contractor. I didn't work inside a building. I worked at hundreds of buildings. So when I would show up to do a service call, whether it was a routine service or an emergency service, I had to park my truck outside the building. So I started outside with my troubleshooting. My systems were water-cooled systems and water cooling systems. I worked on boilers and chillers more than anything else. With my big chillers, what I had cooling towers. Or if they were air-cooled chillers, I had outside condensers. So what did I do? I started at the condensers or the cooling towers because that was logical for me because that's where I parked my truck. Why carry all my tools inside and then find out that the problem's outdoors where my truck is? So it seemed to make sense to me. So I did it a little backwards, but it worked for me. So that was my pattern. Everybody will have a different pattern. It's based on what your work is. So establish that pattern. Figure out the process and the flow that works best for you. And repeat this process the same way every time. That's why I did it from the outside in, because it seemed to work best for me. I'll give you an example. I got a trouble call one afternoon from an airport customer of ours. It was an international airport, and we didn't do the main terminal, but we did the control tower. They had a new water source heat pump system on the control tower, and we'd gotten the contract to take care of that. And that water source heat pump system had a small evaporative cooling tower sitting outside of the control tower. And back in those days, airport security was not what it is today. I was able to drive my truck right out to that cooling tower and start my service right there. And I got a trouble call one afternoon. And my office called me and said, Gary, how close are you to Syracuse? And I said, well, about 20 minutes. What's up? And they said, we got a problem at the airport, and it looks like you're the closest guy. Now, I owned the company. I ran the company, but I was still doing service work right up till the day that I got rid of the company 20-some odd years ago. I still did service pretty much every day because that's what I love to do. And so I was in my truck doing service somewhere and got this call. And I went over and I looked at the cooling tower, and the water flow down through the tower was not consistent. It was heavy on this side, pretty much empty in the middle. There was no water flow in the center. What I found was, and I'd never seen it before, somehow a plastic trash bag had gotten through the fan shroud on the cooling tower, and it was shredded, but it was still pretty much intact, and it was laying up in the top of the spray tower and diverting the water from the center of the tower, and a lot of the water was running out on the ground. That's all the problem was debris in the tower. It took me about 10 minutes to diagnose because of my pattern, because of starting at the tower. So without shutting it down, because I know if I shut the tower down, it's going to shut the airport down. Without shutting it down, I managed to get that obstruction, that plastic trash bag out of the tower. I fished it out of there with a piece of PVC pipe. It was like I was on a fishing expedition. But I got it out of there, went back to its normal operation. I put on a dry shirt because I got soaked doing it. And I always carried dry clothes in my truck. But I put on a dry shirt and I walked into the mechanical room holding this dripping trash bag. And the mechanic that had called me said, what are you doing? And I said, just fixing the problem. And he stood there for a minute and he said, I mean, what are you doing with a trash bag? And I said, fixing the problem. All because of that pattern. And within a few minutes, their temperatures went down, their pressures went back to normal, and they were back in perfect operation. But figure out what the process is that works best for you and follow that process all the time. That way you won't miss a step. It'll streamline your troubleshooting process, and you don't want to deviate from that. if I had started inside that day, if I had parked my truck and then ran indoors and said, hey, what's going on here? Look at the gauges, look at the thermometers. It would have taken me a lot longer to figure it out. So establish a pattern and stay with it. Everybody thinks differently, everybody works differently, but we can give direction, but my pattern won't work for everybody else. Your pattern might not work for your students. So help them develop their own pattern. That's 3. This is a very good part of that pattern process. And this actually came from my buddy Jason. But talk to the on-site personnel. Don't forget to ask questions. Don't forget to ask some questions. So establish that pattern. Is there power to the unit? What about the thermostat setting? What about the ambient temperature? We want to think of all of these things. These are all things that we want to think about as we establish our pattern for how we're going to troubleshoot, because everyone does it a little bit differently. Always do it the same way. Always do it the same way. As I said before, you always want to do it the same order so we don't miss anything. How many times have you heard this? Plan your work and work your plan. That's all part of troubleshooting. That's number 3. Number 4, encourage your students to accept help. Don't be ashamed to say, I don't know. As instructors, we have to say that sometimes. If we get a question, sometimes we have to say, I don't know. I'll have to think about that for a minute. Or I'll have to do some research on that. There's no shame in that. There's shame in answering a question falsely if we don't know the answer, if we don't know the correct answer. So never be ashamed to accept help. It can come from another instructor. It can come from a student. It can come from another technician. It can come from the manufacturer. So just ask for help. Let me give you a little example of that. I have a freezer in my house. A lot of us do. I have a refrigerator with a freezer, but I also have a commercial freezer as well. And it was acting up a while ago. Now, in my service career, I did not work on domestic appliances. I did not work on household equipment. That wasn't my skill set. I didn't do that. I know how they work, but I never worked on them. That wasn't my thing. But I knew from what I was seeing with my commercial freezer that it was too warm inside. I knew that. So my assumption was that it was stuck in defrost. But I didn't want to tear into it. So I called a friend of mine who does commercial refrigeration, a little younger than I am, but he's still out in the trade. And I called Ben up and I said, hey, Ben, when you have a minute, can you run over to my house? I want you to look at my freezer. And he said, why do I have to look at your freezer? And I said, I want your advice. So he came over. He walked into my basement. He looked at it. He goes, that's smaller than anything I ever worked on. I said, Ben, it's smaller than anything I ever worked on. He said, well, I think you need to call Randy. And I said, okay, this is a small area where I live, guys. We all know each other. But Randy's the guy that does domestic refrigeration work. All right. So Ben does commercial refrigeration. I did the bigger stuff than Ben does, and Randy does the smaller stuff. And so I called him up, and he's not younger than I am. He's older than I am. And I called him up and I said, Randy, I need your help here. And he said, what do you got? And I said, well, this is what I told him. I said, I think I said Ben here looking. I said, I think it's stuck in defrost. I said, I advanced the defrost timer, and that seemed to solve the problem, but I just want it checked out. And he came and looked at it, and he said, you did exactly what I would have done. You advanced the defrost timer manually, what's it been doing since then? And I said, yeah, for the last couple of days, it seems to be working fine. And he said, that's what I would have done. Guys, the point of the story is this. I've been doing these things for 50 years, and I was not ashamed to ask for help because I don't know everything about every piece of equipment. And so I asked a couple of friends of mine. I could have asked the manufacturer. They might have been able to give me some direction. I don't happen to have the book for that freezer. I inherited the freezer when I bought this house, but I could have asked the manufacturer. I could have gotten some help from them. They'll generally try to help us as well. I did that a lot when I was servicing my big equipment. We asked the manufacturers quite often. So don't be afraid to accept help and take it where you can find it, including on the internet. There's a lot of good information on the internet. There's a lot of bad information on the internet too, but there's a lot of good information on the internet. So accept help wherever you can get it. Be a little careful with that though. And that's simply because of this. I've seen a lot of misinformation on the internet as well. Misinformation that we don't know where it comes from. But if it comes from a reliable source, if it comes from a manufacturer, a publisher like Goodheart-Willcox, someone like that, then we can accept that as good information, good, reliable information. If it's posted by someone that you don't know, someone that you don't know their experience or where they're getting their information, be very cautious with that. So accept help, but know its source. That's number 4. And then number 5 is practice, practice, practice. You always want to practice. I'm still practicing after 50 years. I'm still practicing being a troubleshooter, and I think I'm getting better. I think I'm better than, well, I know I'm better than I was when I was changing parts, but I think I'm getting better every day. Even though I don't get to work on equipment much anymore, I do most of my work here in my classroom, so to speak, but I think I'm getting better because I constantly practice, practice, practice. Repetition is the key. Repeat it over and over and over again. That's how we learn. Learning something is a process of sometimes memorization. And one of the keys to memorization is repetition. Say it over and over again. The refrigeration cycle. Follow the heat. The burner sequence. All things that we can learn by repeating them over and over and over again. It takes a long time to see all the problems that we find in our systems. I haven't seen them all yet. I'm still working at that. I haven't seen them all yet. But our technicians have to be constantly learning. And so do our instructors. Our instructors have to be constantly learning as well. So practice, practice, practice. That's number 5. So once again, it looks like this. The 5 steps in troubleshooting, the Gary Xavier method is this. Number 1, observation. Always observe the system before you touch it. Number 2, think logically through the problem. Don't start to tear into it until you've thought about it. Think through the problem. Number 3, establish a pattern. Do your troubleshooting the same way every time. That way you won't miss a step. Number 4, don't be afraid to accept help. And number 5, practice, practice, practice. It takes years and years to become a good troubleshooter. I'm still working at it. Hopefully you are too. With that, I like to say thank you. I say thanks to everyone that's helped me over the years to learn the things that I've learned. Thanks to folks like the great people at Goodheart-Willcox that allowed me to do some things with them and share some information that I've learned as well. And thanks to the over 10,000 students that I've had that have taught me many, many things over the years. So with that, Kathy, I'll turn it back to you.
Thank you so much, Gary. As always, you've given a very informative and enjoyable presentation to our audience. I want to reinforce your step number 4 of your 5-step process of asking and accepting help. And I invite our audience to reach out to Goodheart-Willcox for anything you might need for HVAC instructional resources. If you need samples of the textbooks or help with digital content or your learning management system, we're here to help you. If you need that great math book from Gary Xavier, make sure you reach out to us and we're happy to get you a sample of that. So thank you for joining our session today. Gary, thank you for representing Goodheart-Willcox as always. And thank you for helping our instructors to teach those important troubleshooting skills to the students who will eventually become HVAC technicians. So great session and good luck to everybody out there as you continue your HVAC programs.